time for us to do some problems with integration using polar coordinates. Now, the actual integration part is the exact same. It's just integration. We're just changing our variable names. The interesting part is the setup and how do we get to something in polar coordinates. And so learning to set things up comes with practice. Practice, practice, practice. So that means do as many problems as you can. If you're following along with the video, make use of the pause button. You see a problem? Try it out yourself first. See how far you can get. How much can you do? And if you do need help, go ahead, unpause me. I'm still here, and we can work it out together and make beautiful progress. Well, let's begin. Our first problem. Find the integral 0 to pi, integral 0 to theta, pi minus r times r dr d theta. Now, what's the polar part? Well, the polar part is that there's r's and thetas involved. And then you say, okay, well, how do you integrate? And remember, it's the exact same integration. One layer at a time. Iterated integrals still work the same. We're just using different symbols. And we're not tied to symbols. Even though, yeah, we start with x and y, sure, we can do the same thing with r and theta, or with any two symbols that we want. So, what happens? Well, let me think about how would we integrate this. First thing we probably do before we do any integral is clean up the inside. Integral 0 to pi, integral 0 to theta, pi r minus r squared, dr d theta. And we say, all right, now, great, integrate with respect to r, because we integrate one layer at a time, and the inner layer is the r, so we integrate with respect to r. So, we're integrating the inside here. What do we end up with? Well, we end up with 1/2 pi r squared minus 1/3 r cubed. So I'm integrating with respect to r. R is my variable. And I treat pi like I treat pi. Pi is a constant, 3.14159. Evaluate, and we integrate with respect to r. So r equals 0 to r equals theta, d theta. Great. R equals 0. Perfect. You get 0. Plug in theta. This becomes integral 0 to pi of 1/2 pi theta squared minus 1/3 theta cubed, d theta. And now we integrate this. All right. Well, what does this become? This will become 1/6, right? Because there's a half. This will become theta cubed. You divide by 3. 1/6 pi theta cubed minus here 1/12 theta to the 4th, because it will be theta to the 4th divided by 4. And evaluate 0 to pi. Well, the nice thing again, you plug in 0, you get 0. Plug in pi, and we see we get 1/6 pi times pi cubed. That would be pi to the 4th minus 1/12 pi to the 4th. Well, we can put those together. It's like 2/12 minus a 12th, and so we end up with pi to the 4th divided by 12. And there we go. That's our answer. Now you might say, well, what does it represent? Well, for right now, it just says it represents the total of the integral. And it just depends on what the integral was trying to measure. And we will see some applications of integration in the near future. But for now, we just say, look, we were after a number. This is the number. It represents the total of something. And so, say, beautiful. Moral of the story, look, integration is integration. Doesn't matter what the symbol is. It's all in the setup. Well, that's where we're going to need to spend some time and do some practice. So let's do some more practice. Here we go. Evaluate the integral over some region called S, x, y, dA. Where's our region? It's in the first quadrant. It's inside the x squared plus y squared equals 9, and outside x squared plus y squared equals 4. So if we sketch it, we say, okay, x squared plus y squared equals 9 is code for a circle of radius 3. Centered at the origin. So, all right, so I have a circle of radius 3. So I'll mark 3 here. So I'm inside, okay, so inside, but I'm also outside, x squared plus y squared equals 4, and that would be a circle of radius 2. Okay. And we're in the first quadrant. So notice I only put my drawing in the first quadrant, and I didn't go all the way around. So what's our region? Well, our region is kind of this interesting shape here. And all right, so that's where we're integrating over. Now, how are we going to do it? Notice that nothing in the problem said use polar coordinates, but we're probably going to use polar coordinates because that's what we're practicing. What about the problem that says, hey, think polar? Well, to me, when I see this, I say, look at the shape of the region. It has a beautiful description in polar, and a not really great description when it comes to the Cartesian coordinate system, or if you prefer, the rectangular coordinate system. And if you were to integrate this with respect to Cartesian coordinates, you'd have to carve it up into little pieces. You'd have to have square roots of expressions involved. It could be done, but it seems like it would be messy. In polar, what's the description of the region? Well, if you look at our angle theta, now remember, what does theta do in polar? It's talking about the angle with respect to the origin. So you're coming off the positive x-axis, and you're going to go straight up. So our angle for theta, it goes from 0 up to pi over 2. How about for r? Well, for r, you always think about how do you come out from the origin in a particular direction. And for us, we say we're coming out from the origin, and we start at the inner circle of radius 2 and go to the outer circle of radius 2. So we go from r equals 2 to r equals 3. r2 less than or equal to r less than or equal to 3. Now, sometimes I talk about rectangles when we talk about integrals, and that they have nice setups. This is essentially a rectangle for our polar coordinates, because look at all the bounds. They're so nice. They're numbers for upper and lower bounds for both theta and r. So this is the equivalent of a rectangle. In other words, really, really clean. Beautiful, beautiful. Okay, so where do we go? Well, remember, every integral always has 3 parts. There's the region. Okay, we have a pretty good grasp of that. There's the function. We'll do that. And then there's the split up. And for us, when we do polar, when we talk about breaking things up, that's saying, well, what do you do with the dA term? And in polar, it becomes r dr d theta. Okay, so let's start putting things together. So our integral over our region of x, y, dA will become integral. We'll do the bounds in a second. We want to wait to do the bounds until we are confident, or at least comfortable, maybe, with the order of integration. So x, well, x is r cosine theta. Y is r sine theta. dA is r dr d theta. And now we say, okay, now we do our bounds. Outer integral corresponds to theta. So that goes 0 to pi over 2. Inner integral corresponds to r, and that goes 2 to 3. Okay, so cleaning this up, we have, this is integral 0 to pi over 2, integral 2 to 3 of r cubed, because we have r times r times r, and then we have cosine theta, sine theta, and dr d theta. Now, this is a really nice, clean integral. It's the kind of integral you can actually separate. In other words, I can say, hey, I'm going to do the integral of dr and the integral of d theta at the same time, because our bounds are rectangles, in other words, numbers to numbers, And our function, we can say, look, function of r, function of theta. So we could do the following. So look, if you grab everything that has the theta, what is the things that have theta? Well, the d theta, the cosine theta, sine theta, and the integral 0 to pi halves. All right, so that would say, look, integral 0 to pi over 2, cosine theta, sine theta, d theta. And then the other one, okay, that's everything with the r's. The r, the bounds, the function, integral 2 to 3 of r cubed dr. Well, what do we get? We get the following. Okay, if we integrate cosine theta, sine theta, well, how can we do that? We can do a substitution. If we let u equal sine, du is cosine. Cosine theta d theta. So this would become integral 0 goes to sine of 0, which is 0. Pi over 2, sine of pi over 2 is 1. And then the cosine theta d theta is du, and then it's a u du. All right, so that's a half u squared from 0 to 1, which is good. That leaves us with a half. Okay, so first integral is a half. How about the second one? R cubed, well, all right, what would that be? Well, it'd be 1/4 r to the 4th. Evaluate that from 2 to 3. Okay, well, okay, what do we have? A half times a 4th is 1 over 8. Then 3 to the 4th is 3 times 3 is 9, times 3 is 27, times 3 is 81. 2 to the 4th is 16. 2, 4, 8, 16. And we could stop there, but 81 subtract 16, that's not too bad. That's 65. So you end up with 65 over 8. And there you go. That's the answer. And notice it's kind of a really clean answer. And it's not so clear how we would get, to the final answer. If we had done integration in Cartesian coordinates, it would have been messy. And it's kind of amazing that the final answer, it actually didn't even involve any pi's. Because oftentimes we think, oh, there's a circle involved. Hey, maybe something weird is going to happen. But nope, beautiful answer. Wow, cool. Polar coordinates, good stuff. We like it. We should do more. We will. We will do more. All right, so next problem. Find the volume of the solid region consisting of points where x squared is less than or equal to z and z is less than or equal to 4 minus y squared. Okay. Wow. Okay. Now, what's going on? Well, we have some surfaces here. So let's see if we can maybe get a handle on what's happening here. And I wish I could say, this is such an easy thing to visualize, and once you see it, it's so clear. There's bits and pieces that are easy to visualize, but even now, after I've been doing this problem for years, I don't know if I have a full picture of what's going on. Someday I'll be able to learn to print in 3D. Oh, those are the good days. Looking forward to it. So what we can think of is really there's two surfaces, right? There's these two pieces. So we're told z is above x squared. Now notice there's no y involved. Okay, so what does z equal x squared look like? Well, in terms of the picture, if you think of our x, y, z, well, z equals x squared would say what? Well, think of it as just, imagine for right now we set y equals 0. It'd be a parabola. And now you just copy that back and forth in the y direction. Okay, so there's z equals x squared. We've got to be above that. So it's like you took a piece of paper and you fold it up so you have this trough going in one direction. Now, the other one. If you look at z has to be less than or equal to 4 minus y squared, well, what is that? Well, again, notice it's only a function of one variable, only a function of y. And in the yz plane, so you imagine x equals 0, that would be a parabola that opens down, but where you shifted it up. And of course, you're going to copy it back and forth as you go along here. Okay, so we've got to be above this parabola here, but then turn 90 degrees. We've got to be below that parabola. And what do we end up with? Well, the idea is they're going to intersect, and there's going to be some commonality. So somewhere in here, they're intersecting, and they're forming a shape of some sort. How do we go about finding it? Well, let's think about what's going on here. When we're looking for volume, the way we can integrate, well, we use integration to find volume, is we integrate over our region, our height. Okay, so what's the height? The height is from the top to the bottom. All right, that's not so bad. That's a reasonable thing. We even know which one is the top. The 4 minus y squared is above the x squared, because you can see the inequality. 4 minus y squared is above x squared. So the height, okay, that's 4 minus y squared minus x squared. All right, great, good enough. What's the region? Now, this is the part where we have to say, because it didn't specify a region. So the question is, well, how do we figure that out? So when you have surfaces and you want to find the volume between, what we do is we say the region comes from the intersection of the surfaces. So we ask ourselves the question, where do the surfaces intersect? That will indicate what region we need to work over. Now for us, well, that would be when these pieces are equal. When does x squared equal 4 minus y squared? That's the same as x squared plus y squared equals 4. So, in terms of the picture, it says, oh, lo and behold, it turns out that our surfaces are intersecting right above a circle of radius 2. And now we're like, oh, that's cool. So that's why we're going to end up having something involving our coordinate system. That's our our polar coordinates. You say, perfect. This says this is where they intersect, so our region is going to be the things where x squared plus y squared is less than or equal to 4. Aha, aha, ha, ha, ha. Cool, cool. So because we see a circle, polar. Circles are fantastic for integration using polar coordinates. And now we're like, this is exactly the right day to do this problem. So we say our volume is the integral over our region. And now anticipating where we're going. Notice that our function 4 minus y squared minus x squared can be written as 4 minus x squared plus y squared. And then we're going to do dA. So here we go, into polar. We have to switch 4 minus x squared plus y squared in terms of polar. Well, x squared plus y squared is r squared. So 4 minus r squared. Okay, so that's this piece. Remember, we have 3 things to do. The function, the region, how we split up. How we split up, that just says dA is r dr d theta. And now we say, okay, our region is the circle. It's the circle all the way around. So theta, which is our outer layer, goes 0 to 2 pi. And r, which is our inner layer, well, we go from the center of the circle out to the edge, which is at radius 2. 0 to 2. And we're set up. We're ready to go. Woohoo! Nice. Okay, well, this is an integral we can pull apart, so I'll pull it apart. So what do you have? This is the integral 0 to 2 pi d theta. Wonderful. And 0 to 2, multiply the r through, 4r minus r cubed. And, well, I almost forgot my dr. There it is. Haha. It's there, just very tiny. All right, the first integral, 0 to 2 pi d theta, we can do that one in our head. It's theta from 0 to 2 pi, which is 2 pi. All right, great. The second integral 4r is 2r squared. R cubed, 1/4, r to the fourth. And evaluate 0 to 2. When you plug in 0, you get 0. When you plug in 2, you'll get 2 times 4, which is 8. And here, you get 1/4 times 2 to the fourth. 1/4 times 16, which is 4. 8 minus 4 is 4. So this is 2 pi times 4, or a final answer of 8 pi. Done. Done. Wow. Cool, and it's a nice number too. Whole number times pi. Wonderful. And even though we can't visualize it, even looking at the picture, it makes you like, I wish I could draw better pictures. But even though we can't visualize it, we can still do the work, and we can still find the answer. And this says, look, even though problems may not be given in polar, it might be the case that polar is the natural way that the problem pulls you at the end. All right. Now, on a side note, there is something we should have pointed out. Did we end up with at least a positive number? Because when we're looking for a volume, it should be a measurement of something. And so if we had ended up with a negative, we'd be like, uh-oh. Oh. But we did end up with a positive number, so we did good. We did good. All right, great. Well, let's keep going. More problems to do, right? Oh, yeah, more problems to do. So, our next problem. Set up, but do not evaluate. So cool, this is about setup. That's actually the most important thing. The integration is not about the integration itself, it's about setting up. That's going to be the hard thing as we go through and learn about how to get integration going here. So, we're setting up an integral in polar coordinates, which finds the volume for the set of points satisfying x squared plus y squared less than or equal to z, less than or equal to 2y. All right, well, I think based off of the last problem, it shouldn't be too bad. It's a similar philosophy. So what do we have? Well, we really have a couple things going on. Now, this says, look, you have z equals x squared plus y squared, and we can sketch that. That's actually not so bad. It's a very common example we often use. It's the bowl. So, all right, so I'm inside of the bowl. That's what I'm saying here. So here's our bowl. And now there's this other surface that's z less than or equal to 2y. Okay, well, what's that? Well, z equals 2y, that comes here. If you think of it as you have your x, y, z, so z equals 2y would be a very steep line in the yz plane, but then you just copy it back and forth. And so you're slicing. So what you end up cutting out is you end up cutting out some piece of your bowl. So there's this little thing down there. That's what we're after. So that we're below the plane, but we're in the bowl. So it's like we have this little sliver here. And we're trying to find the volume of that little piece. Okay, so that's what we're trying to do. So, great. Well, we have our formula. When we think of volume, we're integrating over our region, our height. All right, and dA. So how do we find the pieces? Well, our height is top minus bottom. We can see that the 2i is the top because look at the inequalities. 2i is above z, which is above x squared plus y squared. So, integral over our region of 2y minus x squared plus y squared dA. So we're almost ready to set things up in polar. In fact, we can do 2/3 of it because we say, look, integral, y becomes r sine theta. So 2r sine theta. X squared plus y squared becomes r squared, and dA, r dr d theta. What don't we have? We don't have our bounds. Okay, so once we get the bounds, we're done. All right, well, let's work on the bounds. Okay, since we're talking about between surfaces, the bounds come from intersections. So we need to look at the intersection. What's going on? We're going to look at when does x squared plus y squared equal 2y? Now, what would that look like? Well, if you rearrange, that's x squared plus y squared minus 2y. So we kind of see it's a circle. All right? When you see x squared and y squared together, circle, it's just sort of a natural gut instinct. And I say, okay, move the variables across. X squared is fine. We need to make the y squared minus 2y somehow into a nice perfect square. All right, we'll add 1 to both sides. So this looks like x squared plus y minus 1 squared equals 1. All right, so picture-wise, it's the circle that looks like this. Okay, so there's our region. Center is at 0, 1. Radius is 1. Now, that's the picture. Of course, we got to translate things into polar. So let's be careful here. For translating to polar, it's easier to start with our formula. X squared plus y squared equals 2y. That is the same as r squared equals 2r sine theta, and you can cancel off an r. So we say, aha, we're going to this curve r equals 2 sine theta. And remember, we always go from the center out to the curve. And so we're ready. Where does theta go from? Be careful. Where does it go? It goes 0 to pi. So I only need to do the top half because that'll capture the circle. If I went 0 to 2 pi, I'd end up tracing the circle twice, which would give me twice the volume I want. That's not good. So theta bounds go with the outside layer because that's where the theta is. Where does r go from? Goes from the center, the origin, out to the curve. From 0 out to 2 sine theta. And we're done. There we go. This integral, if we carried it out, and we could, in theory, carry it out, we have to be patient, but we're patient people. Come on, we're math people. We can do patient things. We'd actually get the volume that we were after. But we don't have to do it. We just have to set up. Woo! All right. Good. Good. Okay, I think we have time for one more problem. One last problem to finish it up. So let's make sure it's a good problem. Find the integral from 1 to 2, integral 0 to square root of 2x minus x squared of 1 over the square root of x squared plus y squared dy dx. Okay, this is, I think there's a couple of things that you look at this. Now, we have the advantage in that we know we're working on problems related to polar coordinates. So we're like, maybe we should do some polar coordinates on this. Yeah, okay, sure. You have the advantage of like, okay, we know that's what we're doing. Suppose you didn't have that advantage. Suppose you just saw this out in the wild. You were walking around one day and you were like, oh my goodness, look at that integral over there. Whoa. What would you do? How would you make progress? Okay, so let's try to understand. Now, before we begin, I will say that there's sort of a nice little blinking signal that says polar, polar, polar. And there will probably be a few more as we go along. But the part that's saying, hey, polar, 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 do you see this square root of x squared plus y squared? X squared plus y squared is an expression which in polar reduces. Really simple. It becomes x squared plus y squared is r squared. And we're taking the square root of that, which would say, hey, in polar coordinates, this would simplify all the way down to be r. And so that's a signal that, oh, we should think about maybe trying polar coordinates here. There should be something else, which the function simplifies in polar. Let's also look at our shape and see what that becomes. So what does our shape do? What is our shape? Well, we read it off. Our outside layer, we are told x goes between 1 and 2. And then our inside layer is y goes from 0 to the square root of 2x minus x squared. Okay. Let's focus on this curve. So y equals the square root of 2x minus x squared. Let's see if we can't figure out what that looks like. We can square both sides to get rid of the square root. Y squared equals 2x minus x squared. Okay, it's starting to feel circle-like because you see an x squared and y squared. So you say, okay, let's move things around. X squared minus 2x, suspicious gap, plus y squared equals something. Now, why did I put a suspicious gap there? Well, I want to have things be perfect squares because that's how circles work. It's, something with x squared, something with y squared equals radius squared. So x squared minus 2x somehow has to be made into a square. Well, okay, complete the square. Divide by 2. Square it means you should add 1. And if we do it to the left, we'll do it to the right to keep things balanced. So it's, it is a circle. X minus 1 squared plus y squared equals 1. So let's sketch our region and see what we have. We get, x minus 1 squared plus y squared equals 1. So it's the circle starting at 1 here. I'm going to just put it for dot. Now, the reason I'm only drawing the top half is because it's y equals the positive square root of 2x minus x squared. So that's the positive part. Now, where are we going? X goes from 1 to 2, and y goes from 0 to the circle. So our region is this part of the circle. Okay, great. Beautiful. And notice, by the way, you might say, ooh, I have this division going on. You might worry, are we dividing by 0? And the good news is we're staying away from the origin, so there's no division by 0 problem here. Life is good. All right, so we're making wonderful progress here. Let's see where we can go. What can we do? What can we do? Well, we said, look, let's do polar because of our denominator will simplify a lot, but also these are circles. Oftentimes circles, you should think polar might work really well with circles. Okay, so let's see what our integral would become. 1 to 2, 0 to the square root of 2x minus x squared, 1 over square root of x squared plus y squared, dy dx. Would become integral. Now, take it carefully. 1 over the square root of x squared plus y squared, that's the function, and that would become 1 over r. Now, dy dx, I want to be careful here. Dy dx is really, that's the way we break up area when we're doing we're doing Cartesian. So what does dy dx translate into? It will translate into, since it's dA, it becomes the r dr d theta. And now we're like, wow, oh, this is fantastic. What do you see? The r's cancel. Nice, nice. Oh, good. All right. Now, so we've got to get our bounds. Oh, okay, the bounds. That's going to be the hard part here. Because the integral, wow, that's about as clean of an integral as you could hope for. Let's do our theta bounds. I like to do the bounds from the outside in, work in. So the lowest value from theta, because we think about theta coming out, would be 0. And then we're going to go up to, as we start swinging around, what will happen is we're going to go until we just barely clip the very top of this. So the question is, what's this angle here that's coming out? Well, if we think of our picture, we went over 1 and up 1. So this is a 1, 1. That's a 45, 45, 90 triangle, which means that our angle is pi fourths. All right, well, that's nice. That's a nice angle. Okay, now, the last part. We got to get our interior bounds. Okay, so, got to think about those. All right, so how will that work? Well, we come out from the origin. We're going to hit our first bounding curve, and then we're going to hit our second bounding curve. So we got to do both the curves. So let's start with our first curve we hit. Now, it is the curve x equals 1. I can't put that here. Why not? Well, these are r bounds. So I have to have r equals to r equals. So I don't have an x equals option. I have to put into r equals. So we start thinking, okay, well, we do know that x equals 1 is the right curve, so we start rewriting it. X is r cosine theta. So r times cosine theta equals 1. Divide by cosine, and 1 over cosine, also known as secant. So that's what we put here. R equals secant theta. Okay, great. Now, the upper bound. That's to the circle. Well, what's the circle? Okay, I'll start with the y squared equals 2x minus x squared. That becomes x squared plus y squared equals 2x. Or r squared equals 2r cosine theta. And you can cancel off an r. So the circle is r equals 2 cosine theta. And that's the upper bound. So we go from secant theta to 2 cosine theta. And that's it. We've got our integral set up. Wow! Cool. Okay, so let's clean this up, and then we'll actually carry out the integral. So 0 to pi over 4, integral secant theta to 2 cosine theta of dr d theta. Now, this is not an integral we can pull into parts. We've got to do it one layer at a time. The inner layer, though, because we're integrating 1, so this is 0 to pi over 4, integral of 1 is r. Evaluate from r equals secant theta to r equals 2 cosine theta. And then we're going to integrate that d theta. Okay, so that's the integral, 0 to pi over 4 of 2 cosine theta minus secant theta. All right, well, we're almost done. So we integrate. The integral of cosine is sine. So 2 sine theta. Integral of secant. Ooh, okay, do you remember that one? It's natural log of secant plus tangent. Yeah. That's that one like it's the weird one, but yeah, we have to know the weird ones too. All right, we're almost done. Let's plug in 0 first to see. Maybe we'll get lucky and it's all 0. Sine of 0, 0. Yes. Secant of 0 is 1. Tangent of 0 is 0. Oh, log of 1 is 0. Good. So when you plug in 0, you get 0. Plug in pi fourths. 2 times sine of pi fourths. Sine of pi fourths is square root of 2 over 2. If you double that, you're left with square root of 2. Minus natural log. Secant of pi fourths is, well, think of cosine. Cosine of pi fourths is square root of 2 over 2. If you flip it over, 2 over square root of 2 or square root of 2. And tangent of pi fourths is 1. So we get square root of 2 minus the natural log of the square root of 2 plus 1. Wow! This is kind of beautiful. No, it's definitely beautiful. What a beautiful problem. Because when you first see it, your sort of initial reaction is like, oh, can we even do it? But then we're like, oh, okay, there's hints, there's suggestions. Polar might make things work. Oh, look, things become beautiful in polar. Oh, and we get a nice answer at the end. A beautiful, beautiful, clean answer. Well, what a great way to finish off our practice for now. And I hope you had fun. I know I did. And keep practicing. The more you practice, the better you're going to be. You're going to become amazing. I know it. And I hope to see you again. Bye.